All right. Well, thank you all for coming, and thanks for inviting me. My name is Umar Syed, and today I'll be talking about the design of BigQuery ML. I thought I should say a little bit about me just to give you some context. I'm a researcher in machine learning at Google. I work in the Research and Machine Intelligence division, which is part of Google AI. I've been at Google for 7 years, pretty long time, and I've been working on machine learning projects, a variety of them all around the company. I've been involved in the design and implementation of BigQuery ML, which I'm going to talk to you about today since its inception. So I'm very familiar with the underlying machine learning algorithm. I am not, however, a database expert. I am not a systems expert. I have been fortunate to work with a lot of really talented database and systems experts. And I'm learning a lot today, and I'm looking forward to learning more later today. But if you have deep questions about the operation of BigQuery, I may not be able to answer them. I just want to calibrate your expectations. All right, so today, we'll talk about what is BigQuery. Just for those of you who don't know, what is BigQuery ML? We'll discuss the design, we'll discuss the implementation, and then I'll try to go over we'll discuss some common questions that come up when I talk about the design of BigQuery ML. And then I'll briefly mention some things that are coming next. And I think one thing that's going to distinguish this talk from other talks that we saw this morning, that we heard from this morning, is that I'll be talking about, I think I'll be speaking at a higher level, basically. Today we talked about how systems and databases work and how they're optimized. I'll be discussing basically an application that's built on top of a database that uses the capabilities of that database to offer additional functionality. So I think I'll be speaking at a higher level of generality. Okay, so in case you don't know, BigQuery is Google's cloud-based database as a service. It's serverless, it's elastic, flexible. You upload 100 rows or 100 billion rows, and BigQuery will take care of all the administration. You just pay on demand per query. And it's a very popular product that Google offers. So I would say that until recently, BigQuery has offered what I would call relatively simple analysis tools, like the kinds of functions that you'll find in any dialect of SQL. So here's an example. I want to compute the average income per state from some census data. Okay, this is the kinds of analytics that BigQuery until recently supported. And our task was to offer our customers more sophisticated analytics like this by extending the SQL syntax that BigQuery supports so that they can create models from their data and then use those models to make predictions. So in this example, the user isn't just estimating averages, he is computing a model that predicts from data a person's income based on that person's characteristics, and then later he can use that model to make predictions. And we wanted, so basically what we're trying to do is we're trying to enable in-database machine learning for our customers. So why do we want to do this? So basically what we identified was what we thought was a gap in the market. There are a lot of products that are aimed at data scientists or machine learning experts. And these products require some technical chops to use, right? You need to have some pretty sophisticated programming skill. You need to know quite a lot about data analytics and machine learning algorithms. Frameworks like TensorFlow, scikit-learn, et cetera, are difficult, and experts in them are rare. And our business customers always tell us that it's hard to hire people with these skills. However, the category of professionals known as data analysts are far more common. And these are folks who are very comfortable in SQL, writing queries, working in, say, the BigQuery UI. These folks are far more common, and we wanted to aim a product at them and give them the ability to do sophisticated machine learning. And another feature that we felt our customers would appreciate about BigQuery ML is it allows you to do sophisticated machine learning without the cumbersome process of moving data in and out of the database. A lot of machine learning work involves first extracting data from a database, training a model, and then putting it back in. We want people to be able to do everything in the same UI that they're comfortable with. I promise the sales pitch part of this talk is going to be over soon. So we launched it last summer. We have quite a few business customers already. Here are a bunch of them. 20th Century Fox actually moved from another cloud service provider to Google BigQuery because of BigQuery ML. Yeah, and it's currently in open beta. So if you'd like to try it yourself, just go to this URL and check it out. And if you have any feedback, we'd love to hear it. Just send an email to this address. Okay. So let's talk about the design. How did we design BigQuery ML? So here's what we wanted when we were designing it. First and foremost, we wanted whatever we built to be adaptable and compatible with the underlying BigQuery infrastructure. We didn't have the resources or the time to significantly redesign BigQuery to support machine learning algorithms. We needed a solution that was tuned and was designed to leverage BigQuery's existing strengths, which are running large-scale queries over massive data sets in a massively parallel way with very low latency. Secondly, we wanted our solution to be completely scalable. So we didn't want to tell our users there were any hard limits on either the size of the data set that they could train a model on or the size of the model that they would be training. So we wanted to easily handle billions of examples of training data that contain millions of features. And lastly, we wanted our solution to be general purpose. So we didn't just want to be able to offer one or two kinds of models. We wanted to be able to offer an entire class of models that can be used to solve an entire class of prediction problems. So as we were surveying the landscape for in-database machine learning, we found a bunch of work. And I think everything that we found could be divided into three categories. This is our own taxonomy. This isn't something that this isn't established terminology. This is just something we came up with. So I would say that all the existing database machine learning systems that have been published, at least, can be divided into integrated systems, UDA-based systems, and pure SQL systems. And I'll go over each of those one by one. So an integrated system is one of these systems where it has a common infrastructure, and the infrastructure is designed to support both sort of ordinary query processing, SQL engine query processing, and also can support iterative machine learning algorithms that require more sophistication. A prominent example of such a system is Shark or Spark SQL. There are other examples. I think Apache Pig would fall into this category. I feel obliged to say that I think Teradata has a product like this, although I could be mistaken. I feel obliged because they're a platinum sponsor, and I feel like I should mention that. And there are others. So that's one category of solutions. But really, for us, this whole style of solution was totally infeasible because, as I said, we had a small team and we were trying to get something to market rather quickly. And so doing some serious re-architecting of BigQuery, which is tuned to process SQL queries, and re-architecting it so that it could handle ordinary machine learning algorithms was totally infeasible for us, at least in the short term. As was integrating in a tightly coupled way Google BigQuery with Google's other machine learning frameworks like Cloud ML. In the short term, that was infeasible for us. There's another approach to in-database machine learning that's quite popular, and we call this the UDA-based approach. And in the UDA-based approach, you implement your machine learning algorithm as a user-defined aggregate. So a user-defined aggregate is an aggregate function. Common SQL aggregate functions, as you all know, are like sum, count, et cetera, et cetera. Some database providers allow users to implement user-defined aggregates, and there was a very influential and popular paper that introduced a system called Bismarck, which implements machine learning algorithms as user-defined aggregates. And I think Greenplum offers the system, and someone else whose name escapes me right now. Yes, Bismarck is part of this MadLib open source library that you'll find as part of many databases. So why didn't we want to take this approach? Why didn't we want to add machine learning to BigQuery via UDAs? Well, there's a couple reasons. One is the style, the architecture for these algorithms is the following. So you've got your data split over many shards. The state of the aggregation is the model. The function iterates over all the examples in each shard, updates the model one example at a time, and then after every shard is done, the models are combined in some way. They're merged together or after. It's just like any other aggregation function. So this has a couple of implications. One is that the model needs to fit in memory on one machine. And that's a constraint of all of these UDA-based approaches. They assume the model can fit in RAM on one machine. And that is not a constraint that we were satisfied with, especially since BigQuery is a shared system. It's used by many, many users, and the memory limits on an individual user are relatively low. Secondly, and this is a bit technical, and we'll come back to this later, but the UDA-based approach of learning a model on every shard by processing examples one by one, one of the assumptions of an aggregation function is that the function that you're computing is invariant to how the data is distributed. But iterative machine learning algorithms, especially the kind that process examples one by one, typically are not invariant to how the data is distributed. And so the performance of the algorithm is rather sensitive to how the data is partitioned, how it's ordered on disk. And this can, if that ordering or that partitioning is pathological, it can lead to poor performance. And we'll come back to that. Finally, the last style of in-database machine learning that we came across is what I'd call a pure SQL system. So in these systems, we can say that the database doesn't know that it's running a machine learning algorithm. The algorithm is implemented as a sequence of SQL queries. And this sequence of SQL queries has the effect of training a model, but the underlying engine doesn't know that it's doing that. And there's no real changes needed to the underlying engine. You just have sort of a driver script that estimates the model via issuing a collection of SQL queries. Work that you see in this category tends to learn models, a rather narrow, limited set of models that tend to be rather simple. So you'll see clustering papers like this. You'll see there's a paper that does learns a kind of model called a naive Bayes classifier, which is a rather simple model. So as I say, the disadvantages of a pure SQL approach, at least the conventional wisdom has been that pure SQL is inadequate for implementing sophisticated machine learning. And the developers of MadLib, which takes this UDA-based approach, here's a quote from their paper: "The portable core of vanilla SQL is often not quite enough to express the kinds of algorithms needed for advanced analytics." But what BigQuery ML is basically evidence that is contrary to this view. BigQuery ML, today at least, is a pure SQL system. So all of the algorithms in BigQuery ML are implemented more or less as a sequence of SQL queries. Okay, so let's get into the implementation. So let's just go over a little background. So BigQuery ML learns a class of models that are called generalized linear models. So a generalized linear model is a model that takes as input an example, and the example is represented by a feature vector, a vector of features. It takes the inner product of that feature vector with something called the weight vector, the parameters of the model. And then it applies something called the prediction function to this inner product to make the prediction. So we call it a linear model because the model depends only on the inner product of the parameters and the features and no higher order terms. And it's generalized because this prediction function can be basically anything you want. So how do you learn a generalized linear model? Well, you collect a whole bunch of labeled training examples. Here the xi's are feature vectors and labels. X is the features, y is the label. And in order to learn the model, you minimize the sum of the losses of each example. So the loss is a function, and this function varies from the model type to model type, that measures the discrepancy between the prediction made by the model and the true label. So generalized linear models are a very old class of models in statistics. Lots of popular statistics packages will estimate a whole variety of generalized linear models. Excuse me. Here are some of them. Yes, now I think maybe at this point it might be good to talk a little bit about, is this class of models really general enough to serve our customers' use cases? So these days the topic du jour is deep learning. Deep models are not linear, they are highly nonlinear. Is linear learning, does it suffice? And so I think our answer to that is twofold, and this is a very common question that we get. So the answer is twofold. One is, I like to say that you can still do a lot of damage with linear models. Up until a few years ago, linear models were state of the art. Our industry, the online advertising industry, was generating billions of dollars of revenue using only linear models. And for many of our customers, linear models are more than enough to satisfy their use case. That's one. Secondly, if you are going to learn linear models, does it make sense to learn them in the database, or does it make more sense to call some external service, do it outside the database, and then bring the model back in? And I think what we're going to argue here is that if you're only doing linear learning, you might as well do it in the database, because database queries are quite amenable to these kinds of algorithms. The way I like to think of it is every database offers some support for very basic machine learning. For example, every database will offer a correlation function, which is basically a one variable linear regression. Every database will offer a quantiles function, which is basically a density estimator, right? And no one argues that you should do that outside the database. So there's some line on that spectrum of complexity from very simple to highly complicated, where you do some of it in the database and you do some of it outside the database. And what we're arguing is that even for the entire class of generalized linear models, it makes perfect sense to do that in the database. Okay, so you've picked your class, you've picked your generalized linear model, you've picked your prediction function, your loss function. How do you train this thing? Many of you may be familiar that the way you train it is via gradient descent. You have this objective, and then you iteratively adjust the model parameters to minimize the loss. Every iteration, you make a small adjustment to walk down this landscape until you find the bottom of that loss function, and that's your learn model. So this is what we do. So in BigQuery ML, gradient descent is implemented as a sequence of pure SQL queries. And the key fact about the system is that in our system, both data and models are represented as tables. So the data, of course, is a table, and that's what the user provides. But we also maintain the model as a table. It's just a list of feature names and their weights. And every iteration, we issue queries that join the model to the table, perform some calculation that amounts to a gradient update, update the weights of the table, of the model table, and write it back to disk. And that's it. So just to give you a little bit of a sense of what these queries look like, here's a somewhat simplified version of the query that we use to update the model weights. Right? So here, we have some macros that represent mathematical expressions, but there's nothing other than being sort of hairy mathematical expressions. There's nothing too computationally intensive going on there. Here's a simplified version of the query that we use to compute inner products. It looks just like what you would expect it to look like, and so on and so on. Okay, so what else can we say about this? I think the number one question that we get, other than why only linear models, is why are you using a batch method? So if you're familiar with trends in machine learning these days, the most popular machine learning algorithms tend to be what we call incremental or stochastic. And the way they work is you have a very large training set. Every iteration you sample just a tiny, tiny number of examples from that training set randomly. And you use that tiny set of examples to update just a tiny fraction of the weights of your model. So both linear and nonlinear models and deep models tend to be trained this way these days. And the reason is that this makes every iteration very, very fast. You need a lot of iterations to train the model, but because each iteration is very fast, overall it's a win. So this is sort of the state of the art in machine learning. But we're not doing this. We're doing a batch method. A batch method is a method that tends to take many fewer iterations, but every iteration looks at every example in the training set and updates all of the weights. So why are we doing that? There's a few reasons. Incremental or stochastic machine learning algorithms, they require a way to efficiently randomly sample from your data set and to efficiently randomly access weights in your model and update them. And if you're a user of BigQuery, you know that currently BigQuery doesn't really have good support for these primitive operations. If you want to unbiasedly sample a small set of rows from your table, you've got to scan the entire table. So that's one reason. Nonetheless, what BigQuery really is good at is performing huge batch operations, massively parallel, very quickly, with low latency. And when you combine that with a batch algorithm, you can still get good performance. So we're still able to train on billions of examples and millions of features in time that's good enough for our customers. I alluded to this earlier. So a batch ML algorithm is much less sensitive to how the data is distributed on disk because every iteration it ingests all of the examples and updates the entire model. Incremental algorithms, because they operate, well, on a single machine, they look at examples one by one, and on different machines, they don't communicate, they only communicate at the end. So they're highly sensitive to pathological ordering and pathological distribution of the data. So one way to alleviate this, if you're doing incremental learning in a distributed system on a large data set, is to just randomly shuffle the data. Right? That's the best way to alleviate this, and then you'll be fine. The trouble is in BigQuery, the data is often not randomly shuffled and is intentionally not randomly shuffled. So our users want to partition the data in a way to satisfy other kinds of queries that aren't machine learning queries. And so this can lead to very poor ordering. So here's an example on a data set where basically it's online advertising data, as you might expect. And there's a lot of features that are both rare but also highly informative. And so when features are both rare but highly informative, they'll only appear on a handful of shards among the hundreds of shards that you're operating on. And when the incremental algorithms are operating independently on every shard and only get to communicate at the end, information about the informativeness of those features takes a long time to propagate to all the other trainers. A batch algorithm looks at everything all at once, has a global picture of the entire, of the model, of the data, and makes much faster progress. Another reason why a batch algorithm is a good idea is that sometimes, in some special cases, you can estimate the model in closed form. For example, consider a linear regression problem where you've got a whole bunch of examples, but not a lot of features. So if you'll remember your linear algebra textbook, there's a formula for estimating the model weights in this case. Here it is. And so what we do is we can just break this up into two operations, one that exploits the parallelism that BigQuery offers and one that exploits the small number of features. So there are some matrix multiplications here that are large, but we can do that in a distributed way by writing an appropriate query. And then once we've done those large matrix operations, we're left with a couple of small matrices, and we have to invert one of these matrices. But that's not expensive because, as I said, in this special case, we're handling situations where there's only a small number of features. And so we can just do that in memory. So for these special cases, we can exploit the structure of the problem and solve the problem much faster, but we have to do that in a batch way. There's a final advantage to batch methods that I wasn't sure if I'd have time to talk about it, but I guess I do. The way to speed up a machine learning algorithm, the best way to speed up an iterative descent algorithm of the kind that we've been talking about, is to get some kind of a better understanding of the curvature of the objective function that you're trying to minimize. So descent methods, they walk slowly down this objective function, and they have an understanding of what the slope of that function looks like, but they don't have a great understanding of what the curvature of the function looks like, because they're local search methods. Any information about the curvature of the function that you can provide to the algorithm helps it get to the bottom of that objective function more quickly. Stochastic or incremental methods, it is very hard for them to get information about the curvature of the function because they don't have a global picture of the entire objective function because they only look at a few samples at a time. A batch algorithm has this global picture, and so you can use techniques that are decades old from optimization to estimate that curvature and then use that to inform the descent and get to the bottom of the objective much faster. So techniques like preconditioning, line search, you may be familiar with some of these. So these are decades old techniques, but they work best in a batch setting. Okay, so we have a lot more coming. I asked, they said I couldn't talk about it because it hasn't been announced. The timing of our conference is a bit unfortunate. If it had been next week, I could have talked about it, but it's not. So we have a lot more functionality being announced literally next week at the Google Cloud Next conference. And yeah, that's all I had. Thanks.